So now that we've looked at how data is actually stored in our machine, so we're using ones and zeros. We've looked at how characters are handled by using the ASCII or Unicode encoding schemes. But how does this communication between a machine and a person evolve over time? So the first thing we need to know is that the machine language for a computer varies by each computer. I could take two completely different machines, and the way they arrange their bits could be very different. In fact, it's very common for the designers of different CPUs to use different sets of binary codes to perform operations. So the way an Intel processor handles certain operations could be very different than how an AMD processor handles it. But the very early computers were programmed in the machine language. So yes, when you're first writing the very first programs, people were doing ones and zeros. And yes, this was a huge pain. Let's take a look at an example of machine language instructions. So let's suppose I want to compute the wage of some person. Now the way we do that is we take the pay rate and multiply it by the hours worked, and that will of course give us our wage. Now in order to do these computations, we have to have these values stored in memory somewhere. So we're going to make a couple of assumptions of the exact memory addresses in this case. So let's just suppose that the rate is stored at address 010001, the hours is stored at address 010010, and the wages is stored at address 010011. So yes, remember, the addresses are expressed in binary. We're dealing with machine languages, so everything is done in ones and zeros. Now we need to do some types of operations in order to compute the wage. So in this case, we're going to deal with three operations. Load, which takes the value in our memory and store it in a register. The multiply will actually work with the values that are in the register. So in this case, we would multiply what's in the register. And then store will take the value that's in the register and put it back into memory. So in this case, let's say we have the binary codes for those operations. So for load, the binary code would be 100100. The binary code for multiply is 100110. And the binary code for store is 100010. So if we put all this together, we would get the following set of instructions. So it looks something like this. Yeah, it looks like a bunch of ones and zeros. So what's going on here? Well, let's take a look at each line. And all we got to do here is just map the binary codes with what we just talked about. So this first line, 100100010001, that is our load rate instruction. So we're going to take the value of rate and we're going to store it into a register. The second line, the 100110010010, that is going to multiply our hours. So that is where we're going to take what's already in our register, which is the rate. We're going to then multiply it by the value that's stored in the hours address. And then the last instruction, the 100010010011, that's going to take the result that's now in the register, because the register has the wage value, but now we need to store it back into our memory. So that first part is our store operation, and then that second part is the address of wages. So that means we're going to take whatever is in the register, which is our wage value, and store it in the address that we have assigned to hold our wage value in our memory. So yeah, programming in pure machine code is not very fun. I mean, imagine trying to do all those ones and zeros. It's quite tedious. So the good news is we've made improvements since then. So we have what's called the assembly language, and this was developed to make the programmer's job a lot easier. Is it perfect? No, but it is a lot better than trying to do it in machine code. So the idea with this is that we take an instruction and we use an abbreviation instead of just using ones and zeros. So we're trying to put words into our instructions instead of the hard zeros and ones. So a couple of different types of operations out there are load and store, and yes, it is STOR, it's not a typo, multiplying, adding, subtracting. So these would be the different types of operations. There are a lot more than that, but these would be the actual operations instead of having some type of binary code. So if we take a look at our earlier example of multiplying the hour and the rate, we would get something like this. So this looks a lot easier to understand than trying to map the zeros and ones with the actual values and the addresses. So we clearly see that the first line is that we would load the rate. The second line means that we would multiply what we have in our memory by the hours, and then we would store the result in the wages. Now, if we want to run a program in the assembly language, we would need what's called an assembler. And what this does is it takes our assembly code and it translates it into the machine language. So remember, the machine still only reads zeros and ones. It cannot read assembly language. So we need some programs, so in this case it's the assembler, that will take our assembly instructions and convert it into those zeros and ones so that way the machine can understand it. Now, assembly languages are great, but once again, they're not perfect. So it'd be nice if there were an improvement from it, and fortunately there is. So high-level languages have been developed to make programming even easier than assembly language or machine language. And these are a lot closer to normal speaking languages. That's not to say that we're writing these languages in complete sentences, but it's pretty close. We're using more keywords, we're using equations, so it's a lot easier to understand. And there are so many different types of programming languages out there, especially at the high level. So we have like BASIC, Fortran, COBOL, Pascal, C, C++, Java, and there are new programming languages being developed to this day. So let's take a look at our earlier example. So if we want to compute the rate in the hours to get the wages, well, this is our statement. That's it. So before we had 3 lines of code that would take care of it, but all that can be done in a single line with a high-level language. Now Java, once again, is an example of a high-level language. And in order for it to run, we have to translate it into an intermediate language. And we call this intermediate language bytecode. And then we take this bytecode and we execute the bytecode, and as it's running each line, it is being interpreted and translated into machine language. So it's a little different from other types of high-level languages where we would use a compiler. So the compiler would take the source code and translate it into machine language code right away. But with Java, what happens is we still use a compiler, but it takes the Java code and converts it into the bytecode. And then when we run that bytecode, it will actually translate it into the machine language at runtime. Now we do need to talk a little bit about Java because it's a very different programming language compared to the other high-level languages. Because different machines, well, they use different languages. So we said earlier that I could put 2 machines together and the way they handle instructions could be very different. What that means is if I want to take my program and compile it into machine language, I can only translate it to a language that a specific machine understands. So if I want to make my same code work on those 2 different machines, I'm going to need 2 different compilers. One to compile my code into machine language for the first machine, and then another compiler to make it work for the second machine. What we would like to have Java programs do is be machine independent. So if I write my Java program and then I can just simply have it run on any machine I want. I shouldn't have to have a separate compiler for every single machine to make my Java program work there. So we wanted to run on different platforms. So we want it to be a more universal language. So what the designers of Java have done is they've created what's called a hypothetical computer. So this is called the Java virtual machine. So the idea with this virtual machine is that we take our bytecode and it serves as the machine language for the Java virtual machine, or the JVM. So what we do is we take our compiler, convert it into this bytecode, and this bytecode is going to be the same no matter what machine or what system you're running this code on. What's different is the virtual machine, and this virtual machine is what takes the bytecode and converts it into the very specific language for that machine.